Welcome back, guys, to the Vaudevillian Veteran cast vicariously as both victim and villain by the vicissitudes of fate. Just had to get that off my chest. First and foremost, I want to emphasize that the highest form of appreciation is not to utter the words, but to live by them. And as a result, the Hacking Time team has become even better. In other news, we have the community video poll I put up a few days ago, asking which video we wanted next, and Wi-Fi won by a landslide victory. This topic is so massive I need to make it into a series, but let's get some groundwork in first in video number 1. So buckle up, turn up those speakers, and let's go. Now, Wi-Fi refers to a family of wireless network protocols that enable modern electronic devices such as smartphones, laptops, and various Internet of Things devices to wirelessly connect to a Wi-Fi enabled router in order to access the internet. Wi-Fi protocols are based on the IEEE 802.11 family, and this is a large family of local area network standards which were developed and maintained by the Institute of Electrical and Electronic Engineers, or IEEE. Try to say that in one shot. Wi-Fi networks, like traditional transistor radios, transmit information over the air using radio waves, which are a type of electromagnetic radiation with wavelengths longer than infrared light. Wi-Fi radio waves are typically either 2.4 GHz or up to 5.8 GHz in frequency. These two Wi-Fi frequency bands are then subdivided into multiple channels, each of which may be shared by multiple networks. For example, when you download a file over the Wi-Fi network, a device called a wireless router or access point receives that data from the internet via an ISP or internet service provider, then converts it into radio waves. The wireless router then emits radio waves into the surrounding area, which are captured and decoded by the wireless devices that initiated the download request. Because Wi-Fi relies on radio waves, interference from other Wi-Fi networks or various electronic applications such as microwave ovens, cordless telephones, refrigerators, transistor radios, Bluetooth, etc. can disrupt Wi-Fi networks daily. So as a network administrator, we frequently have to analyze the Wi-Fi network and its surrounding environment. Tools like NetSpot can be used to visualize, manage, and troubleshoot Wi-Fi connections to ensure optimal Wi-Fi performance. NetSpot can create a detailed visual sort of heat map of the Wi-Fi network, and it identifies areas of signal weakness or identifies potential sources of interference. Even when setting up a basic Wi-Fi home network in this day and age of ubiquitous Wi-Fi networks and Internet of Things homes, a tool like NetSpot is essential if you want an optimal network in that environment. Wi-Fi, as previously stated, operates at the 2.4 GHz to 5 GHz frequency. The 2.4 GHz band is divided into 11 channels, at least in North America, with channels 1 through 6 and 11 being non-overlapping channels. Now I'll get into that much later. The 5 GHz band is divided into a much larger number of channels, with each country's regulations governing how this works and which channels are allowable. The main distinction between the two frequency bands is that 5 GHz signals has roughly half the range of the 2.4 GHz signal. A 2.4 GHz connection travels farther at lower speeds, whereas 5 GHz connections travels faster at shorter distances. Your preference for 2.4 over 5 GHz will be determined by where and how you use Wi-Fi connections most of the time. Now, the 802.11 family of networking standards is quite important to understand, as this determines the speed in which most routers can facilitate data transfers over a wireless network. For example, the 802.11 AC networking standard, which has a multi-station throughput of at least 1 GB per second and a single link throughput of at least 500 megabits per second, is supported by a majority of modern Wi-Fi routers. Many old Wi-Fi routers only support the 802.11n networking standard, which has a maximum net data transfer rate of 600 megabits per second, and only some support the 802.11g networking standard, which has a much lower data rate of just 54 megabits. Now that we looked at the networking protocols, we can look at the networking security protocols that actually secure the data wirelessly. Now, Wi-Fi security protocols protect computers connected to wireless networks from unauthorized access or compromise. Wired equivalent privacy is the most fundamental wireless security standard, which was WEP. It was ratified late in 1997 and declared obsolete in 2004 due to huge security flaws. Now, as WEP was replaced by WPA, the Wi-Fi protected access, which is now WPA2, was introduced swiftly after WEP's failure. WPA2 will be phased out now even sooner for WPA3, which employs even stronger encryption and mitigates the security risk posed by weak encryption and password standards. Now we can dive one step deeper into not only the protocol, but the actual internet protocol that transfers and facilitates data point to point. HTTPS uses an encryption protocol to encrypt communication. TLS stands for Transport Layer Security, but it was previously known as SSL or Secure Socket Layer. This protocol secures communication through the use of asymmetric public key infrastructure. This type of security system encrypts communication between two parties by employing two distinct keys. As the name may render, this key is controlled and kept private by the owner of the website or secure system. This key is kept on the web server and is used to decrypt the data that has been encrypted using the public key. On the flip side of that, we have the public key. Anyone who wants to interact with said server, in a secure manner at least, can use this publicly available key. Only the private key has the ability to decrypt the data encrypted with the public key, thus making the two-point exchange secure. Now, by default, this data transfer occurs over port 443, whereas HTTP, the unsecure version, uses port 80. All secure transfers require this port 443, but the same port also supports HTTP connections. And that's quite important to know. Before a HTTPS data transfer can begin, the browser and the server negotiate the connection parameters via the SSL or TLS handshake, and this is a three-way process. A secure connection is also dependent on this initial handshake. HTTPS prevents websites from broadcasting their information in a way that anyone snooping on the network can easily view it. When data is sent over standard HTTP, however, it is divided into packets of data that can easily be sniffed using any network analysis software. As a result, communication over an insecure medium such as a public Wi-Fi at an airport, a hotel, a public toilet is extremely vulnerable to interception. In fact, all HTTP communications are in plain text, and I'm going to show you this a bit later, making them highly accessible to anyone with the right tools and vulnerable to an on-path attack. HTTPS encrypts traffic so that even if packets are sniffed or otherwise intercepted, they appear as nonsensical characters and can't be easily deciphered. So let's consider the two following examples. So here is the string of text that's completely readable, and here's a string of text passed through HTTPS on port 443 after encryption. With the use of HTTPS, users are protected from the eavesdropping or man-in-the-middle element attack by using this protocol. It can also safeguard legitimate domains against DNS spoofing attacks. To put it simply, any website that requires login credentials or secure data transfer must use HTTPS to protect not only the users, but the data in transit. Now, HTTPS is based on the TLS encryption protocol, which secures two-way communications. TLS encrypts data using asymmetric public key infrastructure, which we looked at earlier. This means it employs two distinct keys. Are HTTPS connections vulnerable to attack? The simple answer is still yes. So despite the fact HTTPS is more secure than HTTP, neither is immune to a cyber attack or social engineering. HTTPS connections can be exploited by the following malicious purposes or technique. Cryptanalysis or protocol flaw. Threat actors may use cryptanalysis or exploit potential flaws in the HTTPS connection to compromise it using cryptographic security systems and gain access to contents of the encrypted messages. Another technique that can be used to attack HTTPS is the computer attacked on the client itself. Bad actors can compromise the HTTPS connection by installing malicious root certificates in the client's computer or browser's trust store and then manipulating the transfers then after. Lastly, we have tampering with the certificate authority itself. So bad actors can manipulate or compromise a certificate authority to obtain a rogue certificate that major browsers mistakenly trust. Now, Wireshark sits at the core of what I'm about to discuss because it sits in the middle when we're analyzing the network traffic, especially when it's over a wireless network. Wireshark is the world's most popular and widely used network protocolling analyzer. It offers a microscopic view of our network and has become the de facto standard for both pen testers and institutions alike. So particularly in the blue team, you may frequently come across encrypted traffic when investigating suspicious network activity. And you might ask yourself why this is. It's because a vast majority of websites use HTTPS protocols. However, various types of malware as well as a majority of websites also use the very same protocol. So for me, knowing what's contained in post-infection traffic when reviewing PCAP files from malware activity can teach you a lot. Having said that, I'll show you how to decrypt HTTPS traffic from a PCAP file using Wireshark. We'll take a look at the text-based log that contains encryption key data captured when the PCAP was originally recorded, which can then be used to decrypt that data. Using this key log, we can decrypt HTTPS activity in a PCAP and examine its true context. So now we're going to head over to my Kali Linux box and examine the Druidex malware infection supplied by Unit 42 and Brad Duncan. They do amazing work. If you want to dive deeper into Wireshark tutorials, I'll leave a link below, but this is the data we're going to look at today. Right guys, now we're back onto my Kali Linux box. We can load up Wireshark. Now Wireshark has been loaded, we can capture data on whichever interface we choose. So we have two here. As you can see, they're receiving packets already, so we can use our ETH0 interface in this case. Double click. Now here you can see this capture icons. You have this shark fin and you have the stop one and you have a restart current capture. So it's already recording and it's already picking up packets from destinations. So while that's happening, this would be a good time to actually try to capture some packets. So if we go to Wireshark's website, for example, first thing we can note here has a secure information certificate. It's because it says the connection is secure. And here we have the certificates provided by whoever their provider may be. In this case, it's Cloudflare. So we know that's secure. Now we can see here loads of packets and different types of information that's arising from just going to that website. So now here we can stop this capture and we can begin examining. The first thing to note when setting up your Wireshark is that you want to set up some of these labels in the columns, as the default ones are quite rubbish, I found. So I made my own profile, as you can see here in the bottom right corner, as Ace, and I have specific columns. If you go to edit and then preferences and then you go to columns, you can see here all of my custom columns. So you could just take a screenshot of this and add your own, because if you just go here and then you could just add your names and you can add the specific type and field examples. These are the filters basically that you put on. So if you take a screenshot of my ones, if you want to copy and go along, now that you have the same columns and filter types I have, we can start beginning dissecting what we captured when we went to that secure website. So if we type tls.handshake.type of handshake and then equivalent to 1, here you will see the HTTPS traffic will reveal the domain name. So in this case, where is the domain name? Here we have some YouTube, and now we have the one we actually went to, which was Wireshark. Fantastic. As a server name for this traffic, when viewed, we can customize the columns. So if you customize the column as I showed you before, you would have this server name field and it will show you the server in which this IP address resolves to and the protocol in which it used to do that. Now, just as a proof of concept for you, we shall look at the port 443. Now, if you remember from what I previously mentioned about port 443, and it's actually secure. So if we right click this and then we try to follow this TCP stream, like I've mentioned earlier, it's just nonsensical text. You won't be able to decipher this because you do not hold the encryption keys. All that is revealed at this point is that there was a response, and this is the domain name response. Anything that we sent to the server is encrypted. To make this encrypted data legible for actually reading, you would need what is called the encryption key log file. Now, the encryption key log file is shown in this example here. These logs are created using what can be a man-in-the-middle technique attack when the PCAP is originally recorded. So when you're actually going to that site and sending that data to that site in that moment of time, and that activity is being recorded, that is the key log for that activity in that moment of time in which it can be revealed. If no such file was created when the PCAP was recorded, you cannot decrypt the HTTPS traffic traveling over port 443 then after. And I hope that makes sense. So what I'm going to do now is load an example HTTPS SSL TLS traffic PCAP and show you what I mean about using the keylog to reveal the encrypted data. Now that PCAP file is loaded into Wireshark, we can use a specific filter to filter out specific traffic as we did earlier. So here we can use the http.request or TLS handshake type equal to 1, which would just show us those two data types and not any SSDP data. So once we've done that, now we can see we're only seeing TLS protocol type and traffic, which is under port 443. Now, just to be clear, this is the infected PCAP file that I will give the link to the GitHub for Unit 42 and the work that Brad Duncan had done on this. But this is the infected PCAP file containing the Dridex malware infection from a random Windows 10 host. All the web traffic, including infection activity, is encrypted with HTTPS, as you can see in the destination. We cannot see any details of the traffic without the keylog file, as I mentioned earlier. Only the IP addresses, TCP ports, and domain names are visible at this point. Now, to reveal the information that we do want to examine, we need that keylog file. So we have the keylog file, and now we're going to import it into this stream to show all the activities, both sides of the channel. So if we go to edit, preferences, then we can go to protocols, and you can see the amount of protocols Wireshark deals with. We want to go to TLS. Now we have TLS, At the bottom here, you can see you have a pre-shared key and then a pre-master secret log file name. We have the file name, so we can load that up, and then we'll Wireshark log file. We'll double click that. That's inserted there. We hit OK, and bang. Immediately, you are seeing the HTTP responses from the corresponding server logs. And we can now see the HTTP requests to Microsoft.com, to Skype.com domains, which were previously hidden, as we saw, inside HTTPS traffic. We also discover the following traffic as a result of the DRIDX infection. So we can see here the Microsoft traffic, the Skype traffic. And if we follow these streams, we can see the corresponding data. Bam. All in plain sight. Now we got here, there's a GET request to a server for a Word document. Tells us the architecture type. It's amazing, and it shows you what channel it's on as well. Tells us the user agent, the encoding type, which is a gzip, amazing. Now if we remove the stream, go back to our previous filter, what we are now looking for is the malicious payloads from the malware itself. So here, for example, now we had foods good for liver, and that might be a load of BS, just like we saw with happened with the Liver King. So let's look at this. All right. What's the corresponding response to that? It's acknowledgement. Go back to our previous stream. Here we go. So we got the request, and then we have a HTTP request, which was the one that we uncovered. It's actually going to a deal file. Damn. So let's follow the HTTP stream. So there's a GET request for the invest deal. Damn, son. Found it. Excellent. All right, happy with that. So now we got that found, and then also we can see there's a post request under here. There we go. There's a post PHP request as well. So if we follow that HTTP stream, here we have it, post request docs PHP. So these two are working in tandem. Let's see, proxy server. There's an exception on the TLS. It's a handshake error and a system call error. But still, it's making a post request to a PH on this server for its PHP file. Fantastic. So as we just saw, the GET request to the liver site, should I say, returned a deal file for the DRIDX, and the post request we also just looked at relates to a C2 or command and control traffic from DRIDX infecting on that Windows host that we're looking at right now. So if we look at this file that we just examined once more to dive in even further, this deal file, we can follow the stream as we did before, but now we could take this one step further. We can actually go to file and then export objects and then HTTP, and now you can see within Wireshark, it will allow us to export the contents of said data packet, basically. Anything inside that HTTP stream we're currently clicked on, we can take. So we want to look at this application stream, which has a file name of this DIL file, so we can examine it. So essentially, we're taking that DIL file, which has that infected malware, and looking at it even further. Save that to desktop. Leave the name as it is for now. That is saved. Lovely jubbly. Now then, now we have this DIL file here. We can go to desktop. Now we can go to file, and now we can examine said file. So invest DIL is an executed DIL for MS Windows. So it can be executed within a Windows system. Let us take this one step further. So if we use the SHA sum of 256 with TAC A against the DIL file, we can see the hash for that file. So if we take this hash, load up a browser, go to Chrome, paste this bad boy in, we can go to any run to see what it has to say about this hash. And bam. It's saying this is Z loader has some malicious activity in the form of a file name called investment stocks. Interesting. And it also provides some evidence of this malware, which is pretty badass. Alright, so essentially it just runs a document that looked like an investment Word document. Here we have a behavior graph, a full flow of the activity. It starts Windows, run CMD. There's no netstat, there's no specs for what it's actually doing. Then it runs that DIL file and executes the DIL file. Interesting. Any run is pretty bloody awesome. Didn't know it goes into this much detail to go in ham. You can see the HTTP requests. We saw some of this already within the PCAP where it goes to Skype. And then it goes to this website again, showing that docs.php file we looked at earlier. Amazing. Shows some of the connections as well that we saw. That's pretty impressive. I'm really surprised how much information we got just from putting that DIL file into a SHA. Amazing stuff. That's a handy tip. So just going back to Wireshark once more, we've demonstrated how to at least use Wireshark to not only examine and decrypt HTTP traffic via the PCAP using also the keylogger file text, but also we've seen that you cannot decrypt HTTP traffic from the PCAP file alone unless you have that keylog file, which in this example was created from the originally recorded man in the middle / demonstration of the file that we was looking at originally. The link to the Hacking Time Discord will be in the description below. Remember to leave positive comments below, and if you can, join the Hacking Time Discord and stay safe in the cyberspace. Peace out.